This is review for chapter 9.7, 9.10 over power series and Maclaurin power series. Uh, so first off, just as review, you're asked to write the first four terms of the series and also provide the general term. Usually what I've seen with students, finding the first four terms is not the issue. It's the general term that's a little bit tedious, but a lot of times on AP exams or also on tests, you're asked to not only provide a certain number of terms, but also the general term, the general rule that can be used to get each of the terms of the series. All right, so these three we definitely need to have memorized: the sine, cosine, and e to the x Maclaurin series. There's a nice pattern here with sine and cosine. Sine has exponents that are odd degrees, so x to the first, x cubed, x to the fifth, x to the seventh, and the denominator factorial also matches the exponents that we see, and the signs also alternate from positive to negative. So here are the first four terms. The general term, notice if we want to have odd numbers, consecutive odd numbers, we need to produce that by 2n plus 1 or 2n minus 1. So first create n is going to keep incrementing by 1, but if we have we're going to create an even number first and then add 1 to it to get that odd number. So 2n plus 1. Now n can either start at 0 or 1 depending on whichever is more whichever you want to use. Usually we choose the n value that will cause the general rule to be the simplest, but you can always test to see whether n equals 0 or n equals 1 will be the easier one to test. In this case, looks like it's going to be n is going to start off at n equals 0. So n equals 0, negative 1 to the 0 is going to be 1, positive number. 2 times 0 plus 1 is 1, so x to the first, and then 0 plus 1 factorial is 1. And then we increment n by 1 to get up to 2, to get up to 1. So it starts at 0, now it's at 1. So negative 1 to the first power is negative 1. 2 times 1 plus 1 is 3. Denominator is same as numerator here, so 3 factorial. So now we're able to arrive at the second term. And then so on and so forth. If we plug in n equals 2, we're going to get the third term. N equals 3 will get us the fourth term. So make sure you're able to, a lot of times to get the general rule, it takes a little bit of guess and check, a little bit of just testing things out, trial and error as well. So this can be a little tedious, but this is required on a lot of different parts for tests and as well as AP exams. All right, if we look at cosine, the rule is similar to sine, similar to the rule for sine, except that the power you see is going to be now even. So think of, also another thing to keep in mind is, you know that sine is an odd function, so we see that relationship. Cosine is an even function, so we see that relationship, 2, 4, 6. Just like sine, we see that there's alternating from positive to negative. So negative 1 to the n, x to 2n, and 2n factorial. So here we want odd numbers, so we get 2n. We use 2n plus 1. Here we want even numbers, so we use 2n. And again, n is incrementing by 1 each time. E to the x has a nice, it's simple to create. What we can do is, you can think of e to the x in terms of the pattern is just each of the terms added together with sine and cosine in increasing order of exponents. So cosine starts with the 1, x is the next term with the sine, x squared over 2 2 factorial, x cubed over 3 factorial. The only thing is that with e to the x, all the powers, all the signs for each term will be positive. And then the rule for the general rule is simply x to the n over n factorial. Now over here, 1 over 1 plus x, this is actually matching with a geometric series. So if we think of it in terms of geometric series, then we can write it in the form of 1 over 1 minus negative x. If we write it as 1 minus negative x, then we can think of negative x as the ratio, and then this a sub 1 is the first term. So if we think of it as a geometric series, first term is 1, and then each term we're going to multiply by the common ratio, which is negative x. So 1 times negative x is negative x, times negative x is x squared, times negative x is negative x cubed. So if we can think of it as geometric series, a lot of times it's easier to create and find the terms for that series. And the general term is simply negative 1 to the n times x to the n, and it does take a little bit of guess and check sometimes to get there. All right, 1 over x, we can also think of this as a geometric series, but if we want to put it into that form, then we need to do some adjustments here. We have to subtract 1 from negative x in order to get it to look like this form, because we want 1 over x is not quite in the form of this geometric series. So in order to get this x minus 1 to show up, we have to get it in that form. So once we have it in this form, because if we were to distribute this through, we're going to see that it's going to end up being the same as 1 over x. But this form is nicer to match with the geometric series. So think of the negative x minus 1 as the common ratio, and the top term is still going to be a sub 1. So 1 minus parentheses, multiply every term or each term by negative x minus 1, and then we see the pattern show up. Natural log of x, we can think of natural log of x as the integral of 1 over x. So the integral of 1 over x is simply just going to be the antiderivative of the series that we just found here. So the integral of 1 would just be x minus 1 becomes x minus 1 squared over 2, and then so on and so forth. Now this minus 1 is actually coming from the fact that if we were to find the integral, we're going to have a plus c, and then if we were to plug in a value that we know is true, 1, 0, we can find that the constant for this antiderivative will be 1. So x turns into 1, and the plus c, the c value ends up being negative 1. All right, let's look at the rest of the first page here. Find the Maclaurin polynomial of degree n for the following. So f of x equals x times e to the 2x. N equals 4. So we want to create terms up to the 4th degree. So we have one. This we can think of it as building in series or building up layer by layer. We know what the rule for e to the x is. So if we write that out, 1 plus x squared over 2 plus x cubed over 3 factorial. Now we can build that step by step. Now to get from e to the x to e to the 2x, we can simply replace every x in the polynomial with 2x. So that becomes 1 plus 2x quantity squared over 2 factorial plus 2x quantity cubed over 3 factorial. And then finally, multiply by x through. And once we multiply x through with the e to the 2x, or the polynomial representing e to the 2x, then we have this expression left. Okay. X plus 2x squared plus 4x cubed over 2 factorial plus 8x to the 4th over 3 factorial. And we look at the pattern here, and we see the numerator is increasing by powers of 2. So 2 to the n, x to the n plus 1 over n factorial. Again, getting to the general rule does take a little bit of guess and check to get. Okay, part B. X over x plus 1. Well, we know the rule for 1 over 1 plus x, or 1 over x plus 1. All right, so then if we were to write out 1 over 1 plus x, which is this rule that we see here, and then we can simply take this and multiply with the numerator of x. If I multiply x through with this known geometric series, then we have this expression and then the general term. All right, number 3, find the Taylor polynomial of degree n centered at x equals c for the following. F of x equals 1 over x. For n equals 5, c equals 1. Now, we could go back and use the rule that we have, but I want us to practice going through the Taylor rule, or Taylor polynomial series rule, which is the nth derivative. Okay, f, you see this n here. This is the nth derivative evaluated at c over n factorial times x minus c to the nth power. So what we need to do is we need to find the fifth derivative starting at f of x. So f of x, f prime, second, third, fourth, all the way to the fifth derivative. So we just simply go through power rule each time. 1 over x. To get f prime, we can bring the x up to the top, make it x to the negative 1, go through power rule, and then continue through all the way to the fifth derivative. Okay, next, we're going to evaluate each of the function's derivative at the c value, which is the center, and this is centered at c equals 1. So we find f of 1, f prime of 1. So we plug the respective into the respective functions and derivatives, replacing x with 1, and we get these coefficients. Okay, so now we're building our Taylor polynomial. So remember, the first two terms is always just going to be your tangent line. So your y sub 1 minus m times x minus 1 plus my coefficient for f double prime, which is 2. So we have the 2 here over 2 factorial, because that's the n value, and then times x minus 1 to the nth. We're just following the rule here. Minus 6, which is the third derivative evaluated at 1, over 3 factorial, because that's our n value, times x minus 1 cubed. And then we go down the line here. The fourth derivative evaluated at 1 is 24 over 4 factorial. And then finally, the fifth derivative evaluated at 1 is negative 120. Okay, we're just following the rule here, right? Replacing every n with the respective number that we're at. So here's n is 5, x minus 1 to the fifth. And then if we clean these terms up, we have the first 5 terms of this Taylor polynomial.